Perfect. Hello, everyone. Hope you had great rest and truly charged with the inspiring talk from Professor Vivian Zhou. Without further ado, let's start our last day of our conference with the first talk, starting with Hwang. Hwang is a fourth-year PhD student at KAIST, advised by Professor Min-Soo Roo. His research focuses on hardware, software co-design for machine learning applications, with a particular interest in efficient GPU systems and accelerated design for large language models. He's also currently on the job market for positions in both industry and academia. So let's give a round of applause for our first presenter. And Rangi, go ahead.
Thanks for the nice introductions. Good morning, everyone. I'm Hwang from KAIST. Today, I'm going to talk about pre-gated MOE and algorithm system co-design for fast and scalable mixture of expert inference. This work is done during my internship at Microsoft Research, collaborating with Jianyu Wei, Shizhe Kao, Changho Hwang, Tiao Tang, Ting Kao, and Mao Yang. First, let me begin with the research scope of this work. This research is regarding mixture of expert model inference from computer system designers' perspective. In recent years, large language models have become widespread, demonstrating remarkable performance in numerous applications, such as chatbot and coding assistant. Consequently, many big tech companies have released their own LLMs, including GPT-4 from OpenAI, Gemini from Google, and Grok from xAI. Looking into these models, we found that most of state-of-the-art LLMs are developed based on the mixture of expert model architecture. You might then wonder what the mixture of expert is and why it is so prevalent in state-of-the-art LLMs. In this figure, we compare the model architectures of the conventional dense transformer and sparse MOE transformer. The only difference between these two transformers is the FFN layer. The MOE transformer replaces the single FFN layer with a gate function and multiple experts, each having the same dimensions as the conventional FFN layer. In this example, we adopt only 4 experts, but in general, number of experts can range from 8 to several hundreds. Now I'll explain how the MOE works with a simple example with 4 tokens. First, in the conventional transformer, the 4 tokens pass through and compute all the layers in a batched manner. On the other hand, in the MOE transformer, the gate function determines the expert activation for each token and route them only to the activated experts. Therefore, the tokens are distributed to the corresponding expert in a per token manner. This unique characteristics of MOE makes the computation requirements for both models are exactly identical, except for a very small amount of computation needed for the gate function. In this figure, we compare the computation requirements of MOE models with different number of experts. The x-axis represents the number of experts in each model, with the number 1 on the x-axis representing the conventional dense model. The computation requirement for the MOE model remains constant, similar to the dense conventional model, regardless of the number of experts. This allows us to enlarge the model capacity to increase accuracy without additional computational cost. However, when it comes to the model capacity, it is almost proportional to the number of experts. As shown in this figure, since the expert parameters takes up a large portion of the total parameters, the model capacity increases with the number of experts. Therefore, the MOE model can require up to 75 times more memory compared to the conventional dense model in our evaluation. Now I will explain the key system challenges of deploying MOE model, which can be caused by its unique characteristics. This figure shows the system hardware and a simplified DNA model with conventional layer. For the conventional model, all the model parameters are usually uploaded to the GPU memory for model execution. However, in the MOE model, since the expert parameters requires much more memory compared to the dense model, we need up to 75 times more GPUs to store the model parameters. It's important to note that even though we need much more GPUs, the computation requirements are still identical to the dense model. This can lead to severe underutilization of the GPUs, and some GPUs may even remain idle as certain experts are not activated because no tokens are routed to them. To mitigate this problem, two types of prior solutions have been proposed, both based on parameter offloading. In the figure on the right, the background color green represents the parameters on GPU, and blue represent parameters on CPU. The first solution, MOE on demand, offloads the whole expert layers to the CPU DRAM and uploads only the activated expert from the CPU to GPU in an on-demand manner in the runtime. This solution can decrease GPU memory requirements. However, the experts are transferred through the narrow PCI bandwidth, significantly increasing inference latency. To address this problem, the other solution, MOE prefetch, similarly offloads the whole expert layers to the CPU DRAM, but prefetches the expert before its execution. However, since the gate function selects which expert to activate right before its execution, there's no way but to prefetch the whole expert layer from CPU to GPU in advance. Prefetching whole expert layer requires large amount of data transfer between CPU and GPU, and occupies large amount of GPU memory, even though most of experts will not be utilized. So far, we can see that the key challenges of MOE arises from the fact that experts are dynamically selected and sparsely activated just before its execution. To holistically address this problem, we propose pre-gated MOE, an algorithm system co-design for fast and scalable mixture of expert inference. The key component of pre-gated MOE is the pre-gate function. We slightly modified the conventional gate function to make a pre-gate function, which enables to select the next block's expert activation from the previous block. This can effectively decouple the expert selection stage and execution stage within the same block, which haven't been resolved by other prior solutions. This decouple of two stages mitigates the impact of the MOE's dynamic selection and sparse activation on its inference performance. For the training of the pre-gate function, it is incrementally trained during the fine-tuning stage. Today's LLMs are first pre-trained on vast amount of textured data for a variety of languages and application domains, which requires a massive amount of computation power. Once the LLM is pre-trained, it goes through the fine-tuning stage with task-specific datasets for specific use cases. Training our pre-gated MOE does not change how the resource-intensive pre-training stage is conducted. Specifically, we utilize existing pre-trained MOE model parameters as is, but changes the model architecture to properly accommodate the functionalities of our pre-gate function. Now I'll explain how the pre-gate MOE works with an example. When assuming the expert 0 is activated for block 0, and it is being executed on GPU, thanks to pre-gate function, we can deterministically select which expert to activate in advance for the next block. In this case, expert 2 is activated for block 1. So we can prefetch expert 2 for block 1, effectively overlapping the transfer latency of block 1 with the execution latency of block 0. This is the latency breakdown comparison between pre-gated MOE and other prior solutions. Firstly, the oracular GPU-only solution assumes infinite GPUs and all model parameters are uploaded to the GPU memory, showing the shortest latency. MOE on-demand offloads MOE parameters to the CPU DRAM, but suffer from extended latency, serializing expert transfer latency into end-to-end inference latency. MOE prefetch tried to overlap expert fetching latency, but failed, since prefetching whole expert layer takes too long time to be overlapped. In contrast, our pre-gate MOE can prefetch only active experts from CPU to GPU, effectively overlapping transfer latency with an execution latency. This yellow highlight shows the latency improvement and expected speedup of our pre-gate MOE. To complete the end-to-end model architecture, we have two special cases for the first block and the last block. For the first block, there's one more additional gate function which selects the first layer's expert activation, and we have no gate function for the last block. Finally, the model architecture will be like this figure, and pre-gate function only selects expert activation within the same iteration. Now I'll explain evaluation result of pre-gated MOE. For system configuration, we utilize an AMD EPYC CPU with 1.8 terabyte DDR memory, an NVIDIA A100 GPU with 80 gigabyte HBM memory, and PCIe version 4, which has a bandwidth of 32 gigabyte per second. For the baselines, we compare our pre-gate MOE with GPU only, MOE on demand, and MOE prefetch configurations. To provide more detailed explanation, GPU-CPU solutions, including MOE on-demand, MOE prefetch, and pre-gated MOE as well, offload MOE layers to the CPU DRAM, while GPU-only solution uploads all the parameters and activation to the GPU. Additionally, in this figure, the known MOE layers include the rest of the layers in the model, such as self-attention layers and conventional FFN layers. Pre-gated MOE achieves comparable accuracy compared to the conventional MOE model for various configurations. We applied the exact same fine-tuning configurations across all model architectures, including pre-gated MOE and conventional MOE. As discussed in the previous slide, the fine-tuning stage utilized the pre-trained weights from the conventional MOE model. For the different model configurations and tasks, pre-gated MOE shows somewhat enhanced or degraded accuracy, but overall magnitude was negligible. This result underscores the algorithmic robustness of our pre-gated MOE. For the inference throughput, pre-gated MOE achieves average 1.5 times and 27 times improvement over MOE on-demand and MOE prefetch, respectively. Furthermore, pre-gated MOE is also able to show 81% of throughput over regular GPU-only solution. For switch large model with 128 experts, since the model size exceeds NVIDIA A100 GPU's memory capacity, it was not able to execute inference on GPU-only solution. Last but not least, in terms of the peak GPU memory consumption, pre-gated MOE consumes only 23% of GPU-only memory usage and incurs only 0.2% more GPU memory compared to MOE on demand. These results demonstrate that pre-gated MOE is capable of reaching the performance provided with the performance optimal GPU only, while also achieving the resource efficiency of the memory optimal MOE on demand, achieving high scalability to deploy large LLMs. To summarize this presentation, we propose pre-gated MOE, an algorithm system co-designed for fast and scalable mixture of expert inference. Our solution adopts the pre-gate function, which deterministically selects and prefetches only active experts of the next block from the previous block. This enables decoupling of expert selection stage and execution stage, effectively overlapping expert transfer latency with the execution latency. Based on this, our pre-gate MOE outperforms other prior works in terms of performance and scalability, as well as demonstrating comparable model accuracy. Thanks for listening to this presentation. I'd be happy to answer any question.
Ramyat from Rain AI. Have you tried using larger models like Llama 3, Llama, like OPT, larger models with pre-gated and seeing the accuracy or perplexity?
Thank you for the question. It's a great question. In our evaluation, we evaluated these types of models for accuracy evaluation. So the base 8 is the smallest model that we. Would you please? Okay, great. So the base 8 was the smallest model, which has the model capacity around several gigabytes. And the large 128 model has model capacity around 100 gigabytes. So we we examined the model accuracy for various types of model capacity from the several gigabytes, from the several hundreds of gigabytes.
Okay, thank you.
I have a question. Do you have a perfect overlap between CPU to GPU when moving your data? Is there some idle time? Does it change from model to model?
So are you asking the transfer latency is perfectly overlapped by the execution latency?
Yes.
Oh, yeah. Actually, it's not, to give more detailed explanation of the switch transformer architecture, there's a transfer blocks are iterated. So the O's blocks are MOE blocks, MOE transfer blocks, and even blocks are just the conventional transfer blocks. So we have more time frame, just not only for the execution of MOE block itself, but we also have the next block, which is the conventional transfer blocks, so a more larger time window to overlapping the transfer latency. It can be different for the different model architectures, but in our evaluation, which is the Google Switch Transformer, it's almost overlapped.
Let's give a round of applause for our author. All right, while they hook it up, let me introduce the next presenter.
Thanks for the introduction. And good morning, everyone. I'm Yubin Qing from Tsinghua University. And it's my honor today to present our work, MECLA, a memory compute efficient large language model accelerator with scaling submatrix partition. I guess everyone here has witnessed the impact of large language models, LLMs, which has become an important part of our daily lives. If we take a look at the development route of language models, at the very beginning, it can only solve specific tasks using word-to-vec. And after the proposal of transformer, people can use pre-trained models to solve various tasks, like filling the sentence, translation, sentiment analysis, and so on. And in this area, GPT-2 and BERT are typical models. And after several years of development, we went into the area of large language model, which can solve general and multimodal tasks using prompt. And researchers find that the ability of language model can be improved by increasing the model size. As shown in the chart on the right part, the language modeling loss can be reduced from 4.8 to 3.2 when the model size grows 100 times. So we can see that the model size has been booming along with the development of the model, and modern LLMs can have several hundreds of gigabytes of weight. Thus, despite being a versatile tool of our daily lives, handling the weight is the crucial issue to using the LLM. Also, the LLM model is distinguished from traditional neural network or transform models like BERT. It generates the output token one by one, and each time, the model takes a prompt and the previous generated tokens as the input and generates a new word, and then the next one. So it needs to fetch the entire model again and again for each word's generation, and we can see from the chart on the right part, the memory access of large language model booms much 10 times faster than the computation. And so we can see that the LLMs are heavily memory bonded, especially in the decoder part. And this chart on the right shows the roofline model of a typical LLM like Llama and the A100 GPU. The compute density of LLM is 0.5 or 1 flops per byte, since it computes 1 token at a time. It works at the memory limitation region of the A100 GPU, which means the throughput of the GPU is limited by the memory access, and the computation unit is not fully utilized. And based on the previous analysis, we can conclude that improving the compute memory ratio is essential to LLM's efficiency. Previous researchers have explored some effective solutions, and we show 3 typical ones here. The first one is the weight quantization. It turns a FP model into int model to reduce the bit width of the weight. And typical practices like AWQ can compress the majority of weight into 3 or 4 bits, which achieves a good compression result. The second achieve is a batch inference. It puts several users' requests together and computes them simultaneously. And another solution is non-autoregressive decoding, which decodes several tokens rather than 1 token at each time. We can see that these methods all introduce more computation with a given amount of memory access. And I would like to talk more about the weight characteristics. Previous algorithm researchers find that only a tiny amount of weight, typically 1%, is crucial to model precision. And it is safe to make aggressive compression like ultra-low bit quantization to the rest part of the weight. They occupy 99% of the weight size but are tolerant to the error, and that is what we focus on in this work. Here, we present a different observation and a solution. It is based on the pigeonhole principle. Think that we are computing an FFN layer in Llama with int8 quantization, and there are a total of 256 possible weight values in the weight tensor, normally from -128 to +127. However, there are altogether 45 million parameters in a single layer, which is far more than 256. According to the pigeonhole principle, lots of weights are duplicated. We analyzed all the FFN layers in Llama 27B and plot the duplication ratio as the right part. We can see that most layers have about 60% of the weights being repeated, and some ones have up to 80%. So this feature proposes optimization potentials. And since there are too many duplications in LLM weight, we find something more than duplication. If a group of values share the same single transformation, they can be viewed as a special duplication. We show a simple example here. There are 4 weight groups with 4 values in each group. And the first 2 weights in W2 can be viewed as doubling the first 2 ones in W1. And similar features can be applied to W3 and 4. In this case, we can use W1 and those shared transformations like doubling, halving, negative, and so on to express the whole weight tensor. Based on this feature, we propose the scaling submatrix partition SSMP method. It splits the weight matrix into several source submatrix and several derived submatrix. And each submatrix contains some weight values. And the derived submatrix can be calculated by multiplying the source submatrix with a scaling factor. As the figure shows, this method exploits 2D weight so-called duplication, and it's both memory and compute efficient. Here, we show a detailed example of the SSMP method. Say we are dealing with a large weight matrix with shape H by W, and we reshape it into 6 blocks. In each block, there are 1 source submatrix indicated with the blue color and 5 derived submatrix indicated with the green color. And each submatrix is shaped 2 by 2 in this example. And so we can see that in block 0, there are originally 24 parameters, but using SSMP, only 4 values for the source submatrix and 5 values for the derived submatrix transformation are needed, which is a comparable compression. And we use a tuple of 4 values, x, y, nx, ny, to express the configuration of SSMP. The x and y indicates the source of each submatrix, and the nx, ny indicates the number of derived submatrix along the horizontal and the vertical axis. In this example, the tuple is 2, 2, 2, and 3. The tuple is closely related to the memory and computation saving and the trade-off between the model accuracy. Also, we use fine-tuning to turn the existing model into SSMP. For more details, please refer to our paper. And the SNP method can effectively reduce the weight parameters, but it requires fine-grained data reuse to achieve efficiency improvements. So we designed a processor named MECLA, which is tailored to SNP. And this slide shows the overall architecture. It contains 1.25 megabytes on-chip buffer for data storage, a P array for tensor multiplication, auxiliary unit for nonlinear functions, controller and DDR, RISC-V controller for chip control, DDR controller for data transmission, and so on. And the PE array contains 8 clusters. And each cluster has 16 sets of 4x4 PEs with dynamic matrix regrouping and partial sum scaling for SNP matrix multiplication. And in our PE array, the smallest unit is composed of 4x4 PEs, which generates 128 bits of the partial sum. The partial sum are further computed by the scaling multiplier, and each partial sum can be multiplied by up to 4 scaling factors. The results are accumulated in the Nair tree, and it also allows the accumulation with a partial sum from other units via a partial sum crossbar to support different SNP configurations. And when we map the weight into the P array, we have 2 modes, the inner product mode and the outer product mode. This is because the parameter of SNP varies from model to model, even layer to layer, and different SNP have different reusabilities. Some have more reuse in the inner product, but some focus more on the outer product. So when more reuse can be exploited in the outer product, we treat them as a common weight matrix, as the light path shows. The 4 output channels can be abstracted with a scaling factor with 1, A, B, C, and 4 weights, W0 to 3. Therefore, we map the 4 weights to the first line of the PE, and the rest lines are for the weights of other channels. And the scaling factors are mapped to the scaling accumulator. But when more reuse can be exploited in the inner product, as the right path shows, we apply a reassociation mechanism, as we can see. We swap the position of the weight and the scaling factor. We map the scaling factor to the PEs, and we map the weights to the accumulators. This feature helps to exploit the partial sum reuse of SNP method. And to measure the performance and the efficiency of our design, we use the following setups. First, we build several models with SNP on PyTorch, and we use the Roberta, Llama, and Bloom models for the evaluation. And for the hardware implementation, we first finished the RTL design with Synopsys design compiler with TSMC 28nm CMOS technology, and complete the placement and routing with ICC. So we see get the actual area of the chip. Then we use the post-layout chip and the model data from PyTorch to perform simulation with VCS and Runtime, which reveals the power utilization and all the working scenarios in details. And this slide shows the chip layout and the breakdown. The chip takes an area of 22.02 square millimeters, and the P array consumes the most of the area, which with 26% for matrix multiplication and about 1/5 for the scaling accumulation. This breakdown is similar to the power one, where P is also the biggest consumer. And we test the computation and memory footprint reduction on the aforementioned models and tasks. And these 2 charts show the evaluation results. With the SNP method and the partial sum reuse, our design saves 65.5% and 69.2% of the computation and memory access efforts. Also, we compare the working energy efficiency of our design and the V100 GPU with different model accuracy degradation tolerance. Our design achieves 34.3 and 48.6 times of varied efficiency improvement, and the peak energy efficiency hits 5.01 and 7.09 TOPS per watt. We further compare our design with previous transformer accelerators. First, please note that the previous works tend to focus on accelerating the attention computation, like using sparsity to save the computation efforts. They perform very well to bird-like models where the input has decent token length, but the attention computation might not be the bottleneck when it comes to LLM computation, because LLM decodes the output tokens one by one, and the weight matrix is rather large. So we can see that our design is the only one that optimizes both computation and memory for the whole model, and it optimizes both for the encoder and decoder models, and it works much better on the latter. Compared to previous designs, we achieve 1.62 times to 18.8 times of efficiency improvement when working at each processor's target models. So let's make a conclusion. Our design offers a memory compute efficient solution for large language model by using the scaling submatrix partition and some matrix regrouping methods. And the innovations collectively achieved an average energy efficiency of 7.09 TOPS per watt, marking a significant milestone in the accelerator design. And that's all for this presentation. Thanks for your attention.
All right, let me ask a question. I have a two-part question. The first one is, how do you determine the right size of the source matrix? How do you determine what is the source matrix is? And the second one, when you get your derived submatrix from the source submatrix, is there any loss that you have to handle? Or is it perfectly non-lossy conversion from source to derived?
Oh, actually, we did we set some search space. We first tested with one model, that is the Llama 27B. We used it as the target model, and we explored the search space. There is a tuple, we say the x, y, and x and y, and we explore it with 2, 4, 8 until 32, each value. And we perform grid search, and there are some pruning and the grid search to first test if there is some accuracy loss of each part and each configuration, which one has better accuracy, or each one has better efficiency. So after this exploration, we can get a brief so-called search space. And then for each model, we performed also some search and a successive Harvey method in the search space and we made the fine-tuning based on this, according to this search space. So in the search space, we have a so-called accuracy limits, and we set there are different matrix for the language modeling task and other BERT-like, we call it like F1 score or FID score. So for different models, there is detailed accuracy loss limitations shown in our paper, and normally for the BERT-like models, it's 1% of the accuracy degradation, but for the language modeling task, there might be more because the FID score is quite low, not so FID, the element score. So, and we showed there are aggressive and the standard two modes of the configurations. One has more accuracy tolerance, but one tends to be more accurate. So there are two sets of configurations in our work. So we call them standard and aggressive.
Hi, can I ask one quick
Actually,
question?
can we make the thing offline? I'm so sorry. Let's give a round of applause to our presenter. For emerging workloads, building efficient AI systems, particularly efficient serving of large language models.
Thanks for the introduction. Hello, everyone. I am Jungi Lee from Seoul National University. Today, I'm going to present our work, Tensor, accelerating large language models via tensor decomposition and runtime requantization. This work was done with my colleagues, Wonbom Lee and Professor Jaeyoung Shin. So this is the outline of today's talk. First, I will explain the challenges in efficient LLM inference and introduce prior works with their limitations. After that, I'll present Tensor, an algorithm hardware co-design for efficient LLM inference. Finally, I'll discuss the evaluation of our work and conclude my talk. Large language models are now one of the most important workloads, but deploying them is challenging because of their growing model sizes and compute requirements. The plot here shows this trend, where the x-axis is the number of operations and the y-axis is the model size. As you can see, compared to the earlier models such as GPT-2, the compute and memory requirements of recent models are about 100 times larger. So the question is, how can we reduce the size of LLMs and run them efficiently? A general approach would be quantizing both weights and activations and running the model in a simpler integer pipeline. For earlier and smaller models, it was relatively easy to quantize weights and activations and use integer compute units. However, for recent larger LLMs, it is challenging to run them in the integer pipeline due to the existence of outliers in activations. When the LLMs scale beyond a certain size, large magnitude outliers appear in a few channels and activations. For example, weight in LLMs on the left shows that values are centered around 0. This makes it easy to quantize weights in LLMs since a small range of values can be easily represented in a low-bit data type. In contrast, activations on the right shows that the magnitudes of some channels are much larger than others. This makes activation tensors much harder to quantize in low-bit data types compared to the weights. These outliers are global and exist across the model layers. The heat map on the left shows the same activation for 5 different layers. Each x-axis represents tokens, or each x-axis represents channels, and the y-axis is tokens. The straight vertical line represents these outliers, and we can see that they consistently appear across multiple layers. So how to handle these outliers in low-bit data type is a key consideration when quantizing activations in LLM. We now discuss why we need to consider outliers when using integer data types. Here, the red dot represents outliers, and the yellow dot represents smaller normal values. We can see that per column groups normal values and outliers together, while per column isolates these outliers. When this group of floating point numbers is mapped to an integer for computation, we set a scale factor to scale the maximum value of a group to a maximum value in an integer. In the case of per row quantization, normal values are relatively much smaller than outliers, so the normal values become 0 after quantization. In contrast, per column groups normal values while isolating outliers, so normal values are more accurately represented by mapping to a wider integer range. We show the quantization results of a 4-bit integer in LLMs. Here, the y-axis is perplexity, where lower is better. Since per column stays close to the baseline, unlike per row, we can conclude that isolation of outliers is crucial for language model performance. Ideally, we would like to use the per column approach that achieves high accuracy, but it leads to a large compute overhead. For example, suppose we apply per column quantization for activation, where each column uses different scale factors S1 and S2, and the weight of a single column is quantized in the same way using a scale factor SW, which is 1 for simplicity. When performing dot product, the multiplication result between the first element is 6, and the second element is also 6. The results cannot be directly added since they represent different numbers 7.2 and 5.4. So all additions need to be done in floating points after dequantization, meaning that the dot product cannot be performed in the integer pipeline and leads to low performance. So the question is, how to split channels and activations without floating point operations? Since per column has a large overhead, per works try different ways to handle outliers while balancing accuracy and performance. We compare these works with a baseline where the entire computation uses an integer processing element. The mixed precision approach represents outliers with more bits. It leads to complex hardware because it requires mixed PEs and often a controller to fetch mixed precision and send to the right PE. Next, recent work uses multiple data types, including custom types to represent outliers. To support these types, it needs an intrusive change for a decoder and extension of PE. In contrast, our approach bridges the gap between the performance and accuracy of the per column approach with a much simpler design. We represent all values in an integer with only a 1-bit shifter attached to the integer PE. So Tensor is simple and non-intrusive to the existing design. Now, I'll present our work, Tender. Our key insight is that even when columns of activations are quantized using different scale factors, we can perform addition in integer without dequantization. This is the same example as the previous one, but now the ratio between the scale factor of columns is an integer 2. Instead of dequantizing 2 6s on the right, we can multiply the first 6 by 2 and share the same scale factor. We call this process rescaling. Since the scale factor is now the same, we can directly add and get the final result. So, if the ratio between scale factors is an integer, it is possible to compute in an integer pipeline without dequantization and floating point addition. Tensor decomposition algorithm groups channels and quantizes each group using different scale factors. While doing so, we set the ratio between the scale factors to be an integer. First, we find the absolute maximum of each channel for a given activation, and then compute the maximum value in a tensor. We then classify each channel into a group based on these maximum values. We first set thresholds, which are tensor maximum, or T, divided by the power of 2. After that, channel maximums are compared with these thresholds and classified into groups. For each group, we set the scale factor based on the upper threshold of the group. For example, we set the scale factor of group 1 using the upper threshold, T, and repeat the process for group 2 and group 3. To reduce runtime overhead, this classification process is performed during an offline calibration. Using the scale factors, we now quantize each column to an integer. Before computation, we reorder columns to ensure that columns with the larger scale factors are computed first. Since the ratio between adjacent scale factors is always an integer 2, rescaling is possible in the integer pipeline. Through the tensor decomposition algorithm, we can overcome the performance challenge of splitting channels and activations by performing the entire computation in the integer pipeline with rescaling. We now discuss how hardware supports reordering and rescaling in the two main components. First is the execution controller. It reorders columns in the on-chip with minimal overhead for the required column group ordering. Second is the multi-scale systolic array for computation with rescaling. In the interest of time, we focused on the multi-scale systolic array and how it performs rescaling. To begin with, we start from the conventional systolic array design. To support rescaling, we only add a 1-bit shifter attached to the accumulator register and a 1-bit rescale signal. So our extension is non-intrusive and allows easy deployment to the existing hardware. At the runtime, skewed activation and rate groups flow through the systolic array. In the case of computing each channel group, the rescale signal is set to 0, and the P performs MAC operation. When each PE finishes the computation of a channel group, one cycle bubble is inserted between the groups, and the rescale signal is set to 1. During the time, rescaling is performed by shifting 1 bit of the accumulated register to the left. This is possible since our decomposition algorithm fixes the ratio between scale factors to integer 2. In summary, the rescaling operation requires only a 1-cycle overhead with a small hardware extension. Next, I'll show the evaluation results. We compare accuracy and performance with prior works on the right side. We use OPT, Llama, and Llama 2 and implement our algorithm in the Hugging Face library. For performance, we implement Tender and Accelerator baselines in RTL along with a cycle-level simulator. We first show the quantization results. For simplicity, we only show the representative results of the two models since others show a similar trend. The number is perplexity where lower is better. Under 8-bit bit width, others do not isolate outliers and group at tensor granularity, resulting in some increase of perplexity. However, Tender isolates outliers through grouping columns and consistently stays close to the baseline. Under 4-bit bit width, Others show a large increase in perplexity, implying that isolating outliers and grouping columns is even more important in lower precision. Tender only shows a small increase in perplexity. Next, we show the performance. In this figure, the x-axis is the evaluated model, and the y-axis is a speedup. Even with higher accuracy, Tender achieves up to 2.6x speedup over the baseline because of its much simpler and denser hardware. Others use mixed precision or custom and multiple types, resulting in area overhead by its complex design and extension of PE. We discussed GPU implementation of Tender as well as how to support rate stationary data flow, so please check our paper for more details. In summary, we propose Tender, an algorithm hardware co-design for efficient LLM inference. By carefully grouping columns considering hardware efficiency as well as accuracy, our approach requires small overhead while achieving up to 2.6x speed over the baseline with substantially higher accuracy. This is the end of my talk, and thank you for listening. I will be happy to take any questions.
All right, let's thank the author if there are no more questions. Great, great talk, thank you. All right, without further ado, let me introduce our next speaker. It's Mohammad Adnan. Mohammad Adnan is a third-year PhD student at UBC, advised by Professor Prashant Nair. His research interest is around architecture and system optimization to tackle the challenges presented by large-scale deep learning models.
Okay, thank you. Thank you, Sumanth, for the introduction. Morning, everyone. I'm really excited to present our paper, Heterogeneous Acceleration Pipeline for Recommendation Systems Training. This work is the result of a joint collaboration between UBC and Georgia Tech. Before getting started, if we take a look at our daily life, we are being surrounded by different recommendation models while using social media, doing online shopping, or while watching movies. These models, they are becoming a really important class of machine learning algorithms because of their ubiquity. Such models, they have evolved over time. Looking at the trends, we can observe that DLRM has turned out to be one of the largest DNN workload with trillion of parameters. Right. From AI infrastructure perspective, they are taking big chunk of data center resources. In fact, Meta reported that approximately 50% of their training compute demand is being targeted towards DLRM training. So given such importance, let's have a look at high-level overview of DLRM. So such models, they comprise of compute-intensive neural networks that process the dense inputs, while the sparse inputs, they are processed using big embedding tables, which are compute-intensive, which are memory-intensive and memory bandwidth-intensive. And these models, they are usually trained either in a CPU-GPU hybrid execution mode, or they can be trained in a GPU-only fashion. For hybrid execution, the GPUs, they are responsible for accelerating the neural network part of the model, while the embeddings being of the order of terabytes, they usually cannot be accommodated within the limited memory of GPU if you have limited number of GPUs, so they need to be hosted on CPU main memory. While in case of GPU-only approach, we have to scale the number of GPUs to accommodate the embeddings on GPU HBM. But both of these training execution modes, they have their own system-level bottlenecks and challenges associated with them. We'll go one by one. So looking at the hybrid CPU-GPU execution mode. So for the both forward and the backward pass, the embeddings and embedding gradients, they needs to be fetched from CPU to GPU and vice versa. At the same time, the embedding lookup is being executed on CPU DRAM main memory. That is low bandwidth. This frequent CPU to GPU communication for embedding and embedding gradient can take up to 30% of overall training time. While if we take a look at the embedding operations on low bandwidth CPU main memory, it is usually 10 times slower in comparison to GPU HBM-based execution because of the higher bandwidth that GPU HBM provides. So these inefficiencies, they directly maps to the system bottlenecks, which are frequent CPU to GPU communication over limited bandwidth PCIe link, and the embedding operation over low bandwidth CPU main memory. While if we take a look at the GPU-only approach, the embeddings, they are scattered across different GPU devices. So we need to fetch all the embeddings from all GPU devices and needs to be scattered across different GPU devices. This results into all-to-all communication collectives, and this all-to-all communication can take up to 50% of total training time, especially when this all-to-all communication is happening across multiple nodes by using low bandwidth interconnects. So this leads to all-to-all communication being the bottleneck, and GPU scaling is another kind of bottleneck in case of limited number of GPUs. So what do we want here? We need a way to minimize the embedding communication for effective utilization of expensive GPU resources and to reduce the GPU idle time. And we want to actually achieve HBM embedding operation execution for embedding especially. And to achieve these goals, we utilize certain key insights. So one insight that we exploit, that is embedding access queue. As our prior work also observed that embedding access is usually skewed towards certain embeddings that result into much higher access frequency, and that results into this kind of power law curve. Here in this graph, we can see that on y-axis, we have the access frequency in log scale, while on x-axis, we have the embedding indices. And we can clearly observe that there are certain embedding indices which are way more highly accessed in comparison to other embedding indices. So we can actually utilize such skewness, or we can actually exploit this skewness to, for an efficient embedding layout across the memories. What we can do is that we can utilize the high accessed embedding to be placed on GPU HBM, while the non-highly accessed embedding can be placed on CPU main memory. But there are certain associated challenges. If we take a look at this skewness within embedding access, this access skew keeps evolving over time. In case of offline training, a certain budget, a certain overhead of static profiling can work to identify such skewness, but in case of online training, a more low-cost dynamic technique is required to identify this evolving skewness and to handle this. While to exploit such skewness, another limitation is CPU-based pipeline scheduler. So if we come up with a scheduler that should segregate the inputs based on this highly accessed embeddings and non-highly accessed embeddings, we need to segregate them. So if we try to utilize CPU-based pipeline scheduler for this kind of segregation, it is limited by the parallel memory access, low bandwidth CPU main memory that results in more than 50% of the GPU idle time that can be seen in this particular graph. To overcome such limitations and challenges, we propose Hotline. Hotline, it's a heterogeneous acceleration pipeline that is complemented by Hotline Accelerator that sits at a PCIe switch. Hotline Accelerator mainly comprises of parallel lookup engine and on-chip SRAM-based embedding access logger. If you take a look at embedding access logger, it's an SRAM-based memory that stores only the embedding indices of highly accessed embeddings. While the lookup engine, it looks up for highly accessed embeddings within a mini batch with parallel lookups into embedding access logger. For further architectural details, please feel free to take a look at our paper for the hotline accelerator details. So usually this hotline heterogeneous pipeline works in 2 phases. The first phase is the learning phase, in which hotline accelerator samples the training data set, tries to find the highly access embeddings and save them in the embedding access logger, only the embedding indices, right? This step is performed once the skewness changes during online training, while in case of offline training, this needs to be done only at the start of the training. The second stage is the pipeline scheduler. So in the second phase, the training is executing in a pipeline fashion that is complemented by the hotline pipeline scheduler. So here we can see the green color shows the GPU execution, while the orange one is kind of like the hotline execution, while the blue one is the data transfer using the DMA engine that we have. Hotline accelerator in the first phase, in the start, it segregates the mini batch into 2 micro batches, popular and non-popular. Popular micro batch comprise of all highly accessed embeddings, while non-popular micro batch comprise of mixture of both highly and non-highly accessed embeddings. Once the segregation is done, the popular micro batch is completely being executed on GPU because all the highly accessed embeddings are available on all GPU devices because we are using the data distributed parallels for highly accessed embeddings. While the popular micro batch is being executed, we fetch the non-highly accessed embeddings from CPU main memory via DMA engine as shown in this figure. This is done by the hotline accelerator. Once these non-highly accessed parameters are available, the non-popular micro batch also executes completely on GPU, and during the backward pass is completely being executed over GPU for the complete mini batch. And when it comes to one another thing is, once the backward pass is happening, hotline takes the next mini batch and pre-processes it. When it comes to the optimizer phase, the highly accessed embeddings, they got updated on GPU devices in a distributed data parallel fashion, while the coalesced gradients on non-highly accessed embeddings, they have been transferred to hotline to be updated on CPU main memory. And the training goes on in this fashion. Moving towards evaluation. For evaluation, we use 4 state-of-the-art baselines. 3 of them are CPU-GPU hybrid execution techniques, while 1 is the GPU-only execution technique. For datasets, we use 4 publicly available datasets, which are real-life datasets. We also utilize certain synthetic datasets for large models. Looking at the performance, so the performance comparison of hotline in comparison to hybrid CPU-GPU-based approach, we got like around 2.4x comparison in comparison to XDL, 2.2x in comparison to Intel-optimized DLRM, and 1.4x higher throughput in comparison to prior work Fei. While if we take a look at comparison with the GPU-only baseline, huge CTR, we got like a speed up of around 1.13x in comparison to huge CTR. One thing to notice here is that for limited number of GPUs, in case of terabyte dataset, huge CTR was not able to train the model because of the limited GPU capacity, while hotline is not limited by the number of available GPUs. In short, hotline, it hosts embeddings across both CPU and GPU memories while achieving HBM-level embedding performance. It hides the CPU to GPU communication under popular microbatch execution and mitigates all-to-all communication. To conclude, hotline solves the communication bottleneck faced by recommendation models training by proposing a data and model-aware pipeline scheduler that reduces the training time by 2.2x, provides a throughput of 2.6x, and it is not limited by the number of GPUs. That's it from my side. Thank you so much. I'll take the questions.
right, let's give a round of applause to our presenter one more time. Our final presenter for the day is going to be August Ning. August Ning is a second-year PhD student at Princeton University, advised Professor David Wensloff. His research interests focus on computer architecture under broad economic constraints such as cost, sustainability, and policy. August will be on the industry research and academic postdoc job market this coming year.
All right. Can I use this? Okay. Buenos días a todos. Me llamo August Ning y es mi placer presentar LLMCompass, enabling efficient hardware design for large language model inference. This work is led by Zhang, who unfortunately cannot be here to present, and done in collaboration with Rohan Prabhakar and Professor David Wensloff at Princeton University. The takeaways of our work is we will present LLMCompass, an open source LLM inference hardware evaluation framework. We'll detail the limitations of existing frameworks for evaluating future LLM inference hardware designs, and we address these challenges to design a fast, accurate, and architecturally expressive framework with flexible model and hardware templates. LLMCompass is a powerful tool for future LLM inference hardware research, and will showcase a case study for throughput-focused hardware designs. Let's begin. As we have seen many times by now, large language models are ubiquitous and have presented new research challenges spanning computer science as well as society. One unique aspect of these LLMs are their sheer size. It's not uncommon for models today to have billions to trillions of parameters, and model sizes have been exponentially increasing. This has led to major challenges for efficient LLM training and inference. A major reason for these enormous models is because model performance scales strongly with compute, dataset size, and the number of parameters. This is previous work done by OpenAI, and we borrowed this figure from their work. So we expect future models to need exponential increases in compute, as well as the number of parameters, to continue performance scaling. And to feed these beasts, we have already seen unprecedented demand on state-of-the-art hardware to run these LLMs. And there's already strong demand for future hardware architectures to continue to improve to keep up with these larger and larger models. When we wanted to get started on researching LLM hardware, we found that existing hardware evaluation frameworks were insufficient to properly as well as efficiently evaluate our proposed hardware designs for these massive models. So therefore, we set out to create our own a new hardware evaluation framework with 3 key features. We want our framework to have fast simulation time, and we also wanted to have accurate simulation, and we also wanted it to be architecturally expressive, which is a term we use throughout this talk to describe a framework which can model a variety of hardware designs, such as GPUs and TPUs. When looking at existing related frameworks, they were all designed with different purposes in mind, and therefore they all had some drawbacks that makes them inefficient for LLM hardware research. For example, roofline models are fast and flexible, but they're unable to capture some of the subtle architectural changes we were targeting. Cycle-level simulators are designed for a variety of GPU workloads. So while they're detailed and accurate, they are often platform-dependent, and they have slow simulation speeds. For example, right now there isn't a single framework which can model an AMD GPU, an NVIDIA GPU, as well as a Google TPU. FPGA emulation is actually able to achieve all of our goals, but is engineering intensive to implement the custom architectures, and we wanted a framework that we could use before having to write any RTL. So when designing our framework, we had these 3 key features in mind. We're able to achieve our goal by leveraging 2 key insights, which we'll go over now. For our first one, let's start by looking at a single transformer layer, which is shown here. And our large language model like GPT-3 are identical stacks of these layers. And then one thing to note is the operators in these transformer layers, such as matmul, softmax, Scalable, and layer norm, are generally dense. So one key insight is that they have regular compute and memory access patterns. So our first key insight is that cycle-accurate simulation is overkill. And we use higher level performance models, which will significantly speed up runtime while maintaining great overall accuracy. Whoops, sorry. Our second key insight is that the bleeding edge LLM inference hardware used for LLM inference all have similar hardware designs. Shown here are 3 flagship products from 3 different vendors. But they all have a notion of a core unit, which will contain matrixly multiply units, vector units, as well as local private memory. And they may be connected to a larger cache or shared memory. And they all have support for device-to-device communication and off-time memory accesses. So our second insight is we could create a generic yet comprehensive hardware template which can model a variety of hardware designs we're interested in studying. With this, let's introduce LLMCompass, standing for Large Language Model, Computation Performance, and Area Synthesis. Let's break down how it works. Users will provide an LLM computation graph, which can be described with provided PyTorch-like API-style API calls, and a hardware description template, which is a parameterized JSON file. Our framework is highly flexible. Users were able to simulate any arbitrary transformer-based model, and users can configure over 40 different architectural parameters to describe their hardware. Our performance model will then simulate the design and also optimize the mapping and scheduling of the model onto the hardware template. This is because we're a hardware research framework. We want to see the optimal performance of the hardware. And the optimizer will try to find the fastest runtime. And this can include over tens of thousands of parameter searches to ensure optimality. LLMCompass also incorporates an area model, which will generate estimated die areas for the provided hardware description template, which enables seamless cost-aware research. To dig a bit deeper into our hardware template, LLMCompass provides users fine-grained control over microarchitecture level details, such as systolic array dimensions and local buffer sizing, architecture level details, such as core counts and memory capacity, and device level configurations, such as device count and device-to-device bandwidth. This allows us to model a variety of hardware for multiple vendors, as well as your own custom designs. We validate LLMCompass against real hardware. When comparing end-to-end LLM inference performance, as well as die area estimates against multiple devices, we were able to achieve great accuracy. Furthermore, we also provide new insights compared to existing frameworks. For example, when we were benchmarking layer norm and we're sweeping the reduction dimension, if we focus on the blue rectangle and looking at the dashed line, that's the roofline, we're able to capture the behavior of real hardware that roofline models overestimate. Additionally, our area model is able to provide core area estimates, which are previously undisclosed. Most importantly, and very importantly to us, LLMCompass is also fast. When simulating a 4-device NVIDIA A100 node running GPT-3 175 billion parameter inference, we're able to simulate in just 15 minutes. And this also includes over 26,000 mapper iteration searches to find the fastest runtime. In comparison, cycle-accurate simulators would take over 6 days to run on our same compute setup. We also model and validate against Google TPU v3 and achieve great accuracy for simulation results. So overall, we were able to achieve our goal to design a fast, accurate, and architecturally expressive simulation framework. We designed LLMCompass for studying future LLM inference hardware designs. So let's go over a throughput focused case study, which will tailor hardware to increase throughput performance. We define throughput as batch size divided by latency. And we define latency as the time it takes to generate all the output tokens. And this can be broken down into 2 stages, the prefill stage and the decoding stage. The prefill stage is before any output tokens are being generated. The decoding stage is when output tokens are being generated one by one. The prefill stage is also known as the time to first token, which is a metric we'll calculate. And you can find the time of the decoding stage by calculating the time it takes to generate each output token, time between token, multiplied by the number of output tokens you have. Batch size is defined as the number of parallel requests you can perform in a single forward pass. So when optimizing for throughput, increasing batch size is memory capacity bound, and decreasing latency is memory bandwidth bound. So existing LLM hardware has had to compromise between having large memory capacity, high bandwidth, as well as low cost, because they generally use a high bandwidth memory, HBM, which is expensive. So we wanted to try a new idea, which we could want to use LLMCompass to evaluate. What if we were to replace the expensive HBM with cheaper CXL DDR memory? Although we would have to trade off memory bandwidth a bit, we're able to significantly increase memory capacity from 80 gigabyte standard to up to half a terabyte. Also, to evaluate this design, we also doubled the number of flops we have in order to keep up the speeds and feeds of compute and memory. To evaluate our design of LLMCompass, we started with a hardware description template based off the NVIDIA GA100. All we had to do was half our core count and then change our microarchitecture, increasing our systolic array dimensions from 16 by 16 to 32 by 32, and then 4x our local buffer size. Then we replaced our memory technology from HBM to CXL and increased the memory capacity. Evaluating our design, we were able to increase maximum batch size by 12 times, and we also able to have an average 1.42 times throughput improvement. And we're also able to decrease our cost by 58% by having a bit of smaller die area, but also much cheaper DDR memory. LLMCompass is a powerful tool for future LLM hardware, inference hardware research, and we're happy to announce that LLMCompass is open source. And we invite you to use, hack, and contribute to our exciting project. Users can get started on LLMCompass by only modifying a few lines of Python and JSON. For example, for our previous case study, we were able to complete it, but only modifying 11 lines of our hardware description template, and 5 of those were for changing out the memory technology. We hope LLMCompass can democratize LLM inference hardware research, where users will no longer require expensive GPUs or powerful compute clusters to get started on validating their hardware ideas. Due to time, we skip out on many exciting details from our paper, so please check it out for more details on our framework, especially on our mapper and scheduler. Additional case studies about the architectural implications of large language models, which includes flop scaling, buffer sizing, and bandwidth scaling. And finally, another latency-focused design, where we maintain 95% of original performance while decreasing die area by 42%. In conclusion, LLMCompass is an open-source LLM inference hardware evaluation framework. From 2 key insights, we were able to develop a fast, accurate, and architecturally expressive framework, and is designed for the future of LLM inference hardware design. Please check out our full paper for more details about our framework, as well as additional case studies, and please check out our GitHub repo to get started on using LLMCompass for your research. Thank you so much, everyone, and I'd be happy to take any questions. Y una cosa más para mañana. Vamos, Argentina! Thank you. Any questions? Okay. Oh.
Hi, great talk, great work. I'm curious, like, is there any insight on how you pick the granularity to model the hardware templates?
Yeah, the granularity for modeling the hardware templates, correct? So one thing we go over in the paper is essentially we say, oh, let's model starting from moving data off of main memory into the global buffer, your L2. Then how do we deal with the tiling and the sizing of moving the matrices into the local buffers? What kind of scheduling we do for multiplying the matrices? So that's sort of the granularity we have, sort of going back to that hardware template. We start by memory or device onto memory, memory into local buffer, global buffer into local buffer, systolic array, and then reading out. So that was our granularity that we were operating at.
Do you think there are opportunities, maybe if you were to go a bit more finer grain, that you would get different architectures, or is it that's because
Yeah. You're obviously correct, but with every performance models, we end up with having trade-offs. I think with the granularity we decided, it was one thing, especially for architecturally expressiveness, we wanted to make sure it was fast enough, and we found great accuracy at the granularity we're involved. But yeah, if we wanted to get a bit more detailed on the microarchitecture customization for future architectures, we would sort of have to hack the performance model and hack the hardware description template a bit. Yes.
Awesome, thank you.
Chen from ByteDance. My question is, why stop at inference? Anything prevent you from expand this work to, let's say, training?
The question is, can we expand this work to training? Stay tuned. But yes, we believe we're going to keep with the hardware description template, but training is just a whole different process, and we found that inference was a great way to get started on sort of validating our hardware ideas, especially we don't really go to like off the node. We haven't modeled infinity band yet, so staying with one single node, we decided inference was the best way to get started. Thank you.
Thank you, August, for concluding that remarkably. For those of you who did not get a chance to ask the authors questions, the poster session just started. Please feel free to go ahead and talk to the authors and ask as many questions as you can. Thank you.
And also a reminder to the presenters in the next session and the session chair to be here in advance so that we can get started on time. Thanks.